from the University of Illinois, Chicago. Dr. Subramanian Sankaranarayanan is an associate professor in the Mechanical Engineering Department at the University of Illinois, Chicago, and he's the group leader in the Theory and Modeling Group in the Nanoscale Science and Technology Division at Argonne National Laboratory. He is also a senior fellow at the Institute of Molecular Engineering at the University of Chicago. Prior to joining Argonne, Dr. Subramanian was a postdoctoral fellow at the School of Engineering and Applied Science at Harvard University. His research focuses on the use of machine learning to reach electronic, atomistic, and mesoscopic scales for accelerated materials discovery and design. He is using supervised machine learning techniques to develop first principle-based force fields for simulating reactive and mesoscopic systems. Other programming efforts include development and use of artificial intelligence algorithms for inverse design of materials and deep learning for integrated X-ray imaging of ultra-fast energy transport across solid-solid and solid-liquid interfaces. His interests span a diverse range of applications from energy storage, tribology, corrosion, to neuromorphic computing and thermal management. He is a co-inventor of 4 patents, and he has co-authored more than 130 journal publications, including several high-impact publications in Science, Nature, Nature Materials, Nature Communications, Proceedings of National Academy of Science, ACS Nano, Nano Letters, and Physical Review Letters, to name a few. With that, I ask you for please give your full attention to Dr. Subramanian and please welcome him to this talk. Please, Dr. Sankaranarayanan, you can start. Thank you so much.
Well, thank you so much, Liliana, first of all, for the introduction. I think it is a great opportunity to share some of the work that we are doing at the Nano Center as well as at my group at UIC. So first of all, before I start, I would like to acknowledge all the postdoctoral fellows who have been involved in building this framework. So some of them are mentioned here. So this is a collective effort between the different divisions at Argonne, and I'm going to talk today about our work on accelerating materials discovery and design using AI and machine learning. So the big questions that we want to answer are: where are the atoms? Can we incorporate simulation into real-time experiments to inform and direct the discovery and characterization process? The second question is, what do these atoms do? Can we make reliable prediction of materials with specific properties? And if you know where the atoms are and what they can do, then the question is, how do you put them there? So can we make reliable prediction of synthesis? And so examples are self and directed assembly, interfacial process, any mode of synthesis that is relevant to achieving desired materials. So what we do at the Center for Nanoscale Materials and as part of my group is to answer these questions with a program in data science for materials discovery and characterization. So broadly, if we want to basically put down our work into different broad buckets, there are 3 aspects to the work. The first one is what we call as predict. So we want to actually come up with models that allow us to predict everything from atoms to devices. An important aspect of predict is to come up with a model that allows for bridging between the different scales. So there are high fidelity quantum calculations which are accurate but are expensive. And then at the other end of the spectrum, you have either the mesoscale models like phase fields or coarse-grained MD, or you have the continuum level models which are very efficient but often lack the accuracy of first principles. So an important aspect is to bridge these different scales. And these could be either physics aware, both informed and constrained, flexible models that allow us to bridge these different scales. So that's an aspect which I'm going to talk about today. The second important aspect is to do a better interpretation. And here, the idea is to actually connect these multi-fidelity models with a corresponding experimental probe. Now, these probes could be either X-ray probes or they could be electron imaging probes. And so Argonne is home to advanced photon source, which is one of the world-class facilities allowing for X-ray characterization. What we want to do is to do better in spatio-temporal resolution than what is affordable to these X-ray and electron imaging techniques. So currently, if you take, for example, one of the techniques known as coherent diffraction imaging, you could do a full 3D imaging, but the resolutions are limited to 10 nanometers. And timescale resolutions are typically limited to picoseconds if you're actually looking at the APS, or if you want to go to the SLAC, which is the Stanford X-ray synchrotron facility, you can do up to a fraction of a picosecond, but still you're limited in the spatial and temporal resolutions you can access. By combining information from the synthetic models or synthetic data with the experimental information that you can obtain from either X-ray or electron imaging, one could actually use the machine learning techniques to get a better interpretation of the experimental characterization. So that is an effort which is ongoing, and I'm briefly touch upon that. And if you can actually make accurate predictions, and if you can interpret the experimental data much better, then the third aspect is, of course, to go ahead and make it. And so synthesis is an important aspect, both within the Center for Nanoscale Materials and in the material science community in general. So being able to realize synthesis and chemical pathways is something that is an important aspect for most of these nanoscale materials design. Towards this end, we are trying to actually use an automated closed loop synthesis. We've started with the polymer films, but then the other aspect that we are interested in is to go beyond the equilibrium phases and carry out inverse design to identify how we can reliably synthesize materials out of equilibrium. So these are the three main aspects that we focus on, and I'm going to touch upon each one of those. The first one, in terms of prediction, I'm going to talk about a specific technique, molecular dynamics simulation. And I'm going to talk about a framework that we have developed, which is called BLAST, Bridging Length and Timescales via an Atomistic Simulation Toolkit. I'll give you an example of water. I'll also highlight the use of AI and machine learning for performing microstructural analysis on the simulation data. It could be experimental data as well, but how can you actually use that for analysis of the data coming out from these large-scale simulations, and some future directions. And then in interpretation, I want to talk about the integrated imaging effort. Two flagship codes that are being developed within Argonne. One is Fantastics, which is integrating microscopy with atomistic simulations. The other one is AI-CDI, atomistically informed coherent diffraction imaging, an example of integrating X-ray imaging with atomistic simulations, and then some future directions. In terms of making materials, we want to actually focus on some of the efforts that we have in phase diagrams, going beyond equilibrium materials. And I will give an example of carbon and tell you what I mean by metastable phase diagrams and what is the vision that we have to construct these metastable phase diagrams. And then I'll give some future directions in that respect. So first of all, let me actually talk about the molecular dynamics simulations. So if you're not familiar with what are molecular dynamics simulations, dynamics, as you know, is basically looking at evolution in time. And molecular dynamics is essentially solving Newton's equation of motion. And there are various different flavors of molecular dynamics simulations. At the lower end of the spectrum, you have the ab initio molecular dynamics simulations, which are limited in the time scales and length scales they can access. They are highly accurate. And for example, if you're interested in the dynamics of a molecule dissociation on a catalyst surface, you can use these AIMD simulations, look at the bond formation, bond breakage events. But they are still limited in the system sizes and timescales that they can access. What you do generally is you introduce the certain approximations to come up with a model that can represent the interactions between the atoms. So if you are interested in a longer time scale phenomena like growth of a 2D material, you resort to what are known as classical molecular dynamics simulations. So here now you can access several tens of nanoseconds and hundreds of nanometers in spatial scales. And you can look at phenomena that are more nanoscale, like the growth of 2D materials on top of a substrate. Then at the other end of the spectrum, you have what are known as coarse-grained models. Here, what you do is that instead of looking at atomic or atomistic interactions, you're now looking at interactions between a group of atoms. And so if you're interested in phenomena that extends over microseconds in time scales and micrometers in length scales, such as nucleation and growth processes, you could basically use these coarse-grained models and carry out those simulations. Now, we have ourselves used these different flavors of molecular dynamics and brought about breakthroughs in the field of tribology. For example, we've used AIMD to design new environmental friendly tribofilms. We have used reactive molecular dynamics to understand this process of superlubricity, which is a frictionless state at engineering scales. And we used MD to actually trace the origin of why this effect is actually observed and to design these solid lubricants. And we've also used coarse-grained MD to actually design these nanoscale membranes and highlighted how there is a small asymmetry in the ligand distribution when these membranes actually form at an air-water interface. And that has interesting implications for the mechanical properties of these membranes. So those are the things that we have actually done, where we have individually used these different flavors of molecular dynamics. But then there is a catch in this, in that as you go up in time scales and length scales, we gain in efficiency, but that efficiency comes at the cost of accuracy. And so one of the things that we are interested in is to seamlessly bridge these different scales. And we want to be able to do these coarse-grained molecular dynamic simulations, but with the fidelity of first principles calculation. The other important aspect why we are interested in developing this machine learning framework is that the ability to develop these force fields or to describe the interactions between the atoms is often limited to a handful of research groups. So there are a few research groups in the world that actually develop these force fields. And then there's a large community of users that is interested in using these force fields. And often there is a large, there's a lot of time that is actually spent on developing a force field for one particular system, which is the reason why nobody really wants to actually get into the development aspect. But often there are scenarios where somebody wants to compute a property, for example, thermal conductivity, but is unaware that the phonon dispersion for that model is bad, which means that it should not be used to compute thermal conductivity. But you can still put in those parameters into lamps and carry out a simulation, and suddenly you get a published article that talks about a hybrid material with extraordinary thermal properties. So what we want to do is to avoid these situations, because if it is a wrong model, then it is basically garbage in, garbage out. And we want to empower users to develop their own force fields so that they can actually use it in scenarios that is of interest to them without actually making this mistake of using it in places where it is not supposed to be used. So we want users to develop their force fields, validate their force fields, and then have a user-friendly way in which they can start developing their own models for carrying out these molecular dynamic simulations. The other aspect, which is important as we are going forward, is that if we take a look at the architectural changes that are taking place. So currently we are at petascale, and we are moving towards exascale computing. If we take a look at the number of atoms or systems that can be simulated, this is for a benchmark system using an embedded atom, all atom MD simulation. We will gain significantly in our ability to simulate larger scale. So if we are able to simulate 1 billion atoms today, we can actually simulate 1 trillion atoms in the future. But if we look at the time scales that we will gain, It is not significant. It will only gain marginally in the timescales, and that is because the clock speeds and bandwidths are not increasing substantially as the architecture is changing from the petascale to exascale. So timescale challenges in the molecular dynamics simulations are still going to remain critical. And to address that, one of the ways is to actually go towards more coarser grain simulations, but more accurate coarse grain simulations. So that is one of the issues that we have in terms of addressing the timescale challenges. So what are the problems with existing force fields? So we want to basically highlight a couple of examples. This is a lithium silicon system which has a mixed ionic covalent characteristics. If you compare the cohesive energies for various different configurations that are highlighted by these red dots, so these are values obtained from DFT, and these are values obtained with a modified embedded atom method, which is a very powerful MD model that typically works for most systems. If there was a correlation between the model and the DFT, you would have actually seen this lying on a straight line. But the scatter just tells you how bad this force field is. And that is one of the problems that we face when we are especially dealing with more complex systems, especially ones where there are mixed ionic covalent characteristics such as the lithium silicon. The other aspect is dynamics. So we have basically a thermosensitive polymer that is undergoing a collapse from a coil-like state to a globular state above its lower critical solution temperature. So this is an expected behavior. Above the LCST, or the lower critical solution temperature, this polymer will undergo a collapse. All the 4 force fields that we simulated, this same polymer, show the expected behavior. But the dynamical evolution is completely different depending on what force field you use. So with all these time resolve techniques that are now coming up, the question is, which one of these force fields are you going to trust? So there are some limitations that we have identified, such as the use of predefined functional forms, forces that are not included in fitting. So that is a problem because there is no guarantee that the dynamics you are actually predicting is correct. If you actually take a look at force equals mass into acceleration is essentially what you are doing. And if the forces are not correct and the model is not trained to capture the correct forces, then the dynamics automatically is not going to be correct. That's one aspect. The lack of adequate training data sets with an overemphasis on equilibrium structures is another, and use of least squares, which is prone to difficulties with convergence and overfitting, and lack of quantitative cross-validation, which is typically not something that is used for developing force fields. So to address these, what we have done is to come up with a framework called BLAST. And what BLAST allows us to do is to pick a model depending on the type of interaction, generate a training data. And so we could be either use experimental data if it is available, or use electronic structure calculations to actually generate training data sets that could be either nanoclusters or bulk properties or surface properties and so on for films. And then the third step is parameter optimization. So once you have your model and training data, you could actually do the parameter optimization using a combination of global and local optimization. So we essentially have options for either performing an evolutionary search, or more recently we've been looking into and we have implemented more AI guided approach for parameter optimization, which is Monte Carlo tree search with reinforcement learning. And then once you actually have come up with a decent set of parameters, we then do a local optimization by performing a simplex or by using Levenberg-Marquardt to actually come up with the best set of parameters. So let me give you an example of water. And the reason we were interested in water is because there's been almost 5 decades of work with various different people trying to come up with models for water. It's an abundant system, but extremely difficult system to look at from the perspective of computational modeling. The reason is because water has a density maximum at 4 degrees centigrade. The density of liquid water is higher than that of ice. So ice floats in water. We have pipes bursting during winter is because, the ice densities are lower, something that is actually very different from normal solids, where the solid density is higher. So these interactions between the water molecules, both intramolecular and intermolecular interactions, are often very hard to actually capture for any computational framework. What we did is that by using our framework, we came up with this model called the bond order potential, the one that you see in blue. And for comparison, we have the experimental data that is actually shown in black. You can see that this model that we have developed is able to capture all these different features of liquid water and for ice. So, when you look at the density as a function of temperature, this model captures the features much more accurately than the best models that are actually available. And that is basically because of the data-driven approach. We took an elaborate training data set, and by following this procedure, we were able to come up with this new model. And so this is a huge improvement over state of the art. And this is something that one can extend to other types of systems as well. But water is just an example where people have been trying for decades to capture these simple properties, something as simple as the locations of the correct melting point and the temperature of maximum density was often difficult for people to capture. And so this use of machine learning has shown that one can actually come up with a better set of parameters that can actually capture all these features. The important aspect about this model is that it is a coarse-grained model. So the model is 2 to 6 orders of magnitude cheaper than the best available non-polarizable or polarizable model respectively. And what that means is that now you can use these efficient and accurate models to look at phenomena much beyond the homogeneous nucleation of ice. So if you take a super cooled water that is at 210 Kelvin, you can actually not only watch the nucleation of ice, but you can also look at how these ice creams form and grow, and features such as how the stacking disorder ice actually forms. And there is a very intricate Ostwald ripening process that happens in the case of ice for the coarsening of these ice grains that is different from what you typically see in the case of metals and ceramics, where the grain growth often happens by just the grain boundary migration. So this is an example where we have integrated atomistic and mesoscopic scale, in the sense that we took the training data from the best available non-polarizable model and then supplemented it with experimental data where the model was actually found to be lacking, and we built a new model on top of that. And so just an example of integration of atomistic and mesoscopic scale, but that is not the only system we have looked at. We've looked at gold clusters, metallic system. We've looked at iridium oxide, an oxide system for which there was no potential. We've looked at 2D materials such as stannine, a material that was actually discovered like 3 years back, and we were able to come up with the potential within 6 months of its discovery. Zirconium nitride, nitride system for which we used a multi-objective search. Cobalt carbon, for which we actually looked at modeling the interactions with a single framework, a heterostructure system. Essentially what we have done is brought down this time frame for force field development from several years down to weeks or days. So that is an important improvement, like advancement in model development that has happened recently. What we want to do is to further leverage this, so we could actually now go beyond the evolutionary optimization, look at more advanced methods that are available, such as the Monte Carlo tree search, that actually became popular after its success in the computer Go game, when it beat the South Korean champion. So what we did is that, when you are using MCTS for board games, you're operating in a very discrete space, in that you are actually going from one place to another, which are discretized. But material science problems are often, continuous. And so you have parameters that actually take continuous values, and likewise functional forms, or, so materials problems are often continuous action space problems, and it is a challenge to actually translate these AI algorithms to operate in a continuous action. So what we did is, without going into the details of what changes we made, we were able to bring about changes in MCTS, and we made comparisons to the genetic algorithm-based search. And what you did is looked at different trial functions, and MCTS actually outperforms GA in all the tests that we actually did. It basically finds a better minimum, and it is able to do that in fewer evaluations. So clearly, one can use MCTS for exploration of potential energy surface. So what we now did is that we went ahead and developed a force field for 55 different systems that had explicitly included training data for nanoclusters from DFT. And we came up with a model for 55 elemental systems. The process actually only takes few hours to optimize potential, and can be done on a single core, meaning that you can actually use your laptop to train force field parameters. So this is highly efficient and basically brings about this new era where we can do a high throughput training of force field parameters. So that's something that is a remarkable advance, we feel. We want to actually go ahead and then also perform microstructure analysis for these large-scale simulations that we are doing. So one of the things we found when we were carrying out these large-scale MD simulations of grain growth is that there was no algorithm available which would allow us to actually look at classifying these grains in full 3D. And so to address that, what we did is that we came up with this algorithm that allows for grain boundary classification, essentially takes advantage of some image processing and unsupervised machine learning, such as the clustering algorithm, to identify these domains which are grains. So you do these filterings to remove these stacking faults or any other defects, and then you do a clustering to actually identify the grain boundaries. The advantage of that is that as you are performing the simulation, you can actually do the analysis of how many grains are actually forming, whether they are subcritical, whether they are critical. And so you can actually map the grain size distribution in real time. So this is actually real-time in situ visualization as you are carrying out these large-scale multi-million molecule or billion molecule simulations. This actually takes only a fraction of a second to do the analysis of the frames. So this is very, very efficient and can actually rapidly analyze these different grains. So what we are doing is now to actually build this framework where one can actually have the flexibility to either generate the training configuration or train the functional form for materials that they desire. So if you're interested in this framework or using it, please feel free to reach out to us. One of the things which we're also doing is that we actually have a computing cluster in-house that allows us to actually generate a large amount of electronic structure data. So we have very standard electronic structure codes which allow us to generate a lot of training data, and these are data generated by our users. And some of the things that we are doing is to actually implement an active learning framework that allows us to continuously generate ML potentials and have a database of these ML potentials. So once you have these atomistic models or coarse grain models, what can you do with it? So the question is, if we want to use and deploy these, there are a few applications, and I can talk about those. So one of them is integrated imaging. One of the visions that we have is to actually be able to interpret better in either microscopy or X-ray imaging than what is affordable to microscopy and X-ray techniques. So what we are doing is, along with my colleague Maria Chan, who's developing Fantastics, is to combine information coming in from the BLAST framework. And so you have now a physics-based information that is used along with computer vision to basically do better in spatiotemporal resolution. And I will give you an example from my colleague, Maria Chan. Basically, this is a typical microscopy image that you obtain for a cadmium telluride interface. And what you're doing is now synthetically generating different interfaces, and you're trying to actually use computer vision to match how the images and come up with atomic locations. But in addition to just looking at an interface matching or pattern matching, what one can do is to actually use information from the physics of the interface. So you have a MD model that is also having that is also giving you information on the energetics, and so the cost function now includes the most energetically favorable interface as well as the best match to the low resolution TMA. So once you actually have this optimization done, you have now a complete visualization of the actual interface that is the most physically viable as well as the best match to your low resolution image. And this is basically a very powerful technique to automatically reconstruct images from microscopy. The other example that I want to highlight is something that we are doing along with a colleague of mine at the APS, Matthew Cherukhara, looking at coherent X-ray diffraction imaging. And the idea here is that the coherent diffraction imaging can be used to image in full 3D the lattice strain in these nanoscale materials. And it can do it operando, so in that it can do it in a pump probe manner, and we can track materials evolution in time. The challenge with using these kind of X-ray or synchrotron facilities is that often a user will go to these synchrotron facilities, carry out their measurement, come back and analyze that data. There is a very tedious phase retrieval algorithm that is involved in reconstructing. So the idea is that, you know, in these experiments, one generally does not have information about the phase. And so what you do is that you only have information about the diffraction patterns, or you have reciprocal space information. Now you want to actually reconstruct this configuration from this reciprocal space information, and because you have no phase information but only intensity information, you are trying to actually follow an iterative procedure to come up with this reconstruction. That is very tedious, and that's why people actually almost always post-process their data. What my colleague did is that, you know, he basically trained on synthetic data that we actually obtained from MD simulations. You can actually generate diffraction patterns from MD, and by training a neural network to replace this phase retrieval algorithm, what one can do is now actually, when you have an experiment where you are heating a nanoparticle, that is a core shell nanoparticle with a laser, and you're measuring this diffraction pattern, you can compare that with a pre-computed MD simulated diffraction pattern database, and then figure out in real time how the shockwave propagation is happening. And so you can go from experimental data to directly visualizing it in real time. And that is something that will allow people to now make changes to their experiments while they are actually doing it at the synchrotron facility. And given how intense the competition is for access to these synchrotron facilities, it is important that we actually are able to provide more real-time feedback, and that is an area that we want to actually focus on. We also want to generalize this to other characterization modes, different microscopy, X-ray, Raman, STM, you know, other kinds of modes that are basically giving us information about the atomistic structure. Okay, so I've spoken about the predict and interpret aspect. Let me now actually chat a little bit about what we do in the area of synthesis. An area of interest for us is looking at materials beyond equilibrium. So in this respect, I think somebody's microphone is on. Can you please mute yourself? Can you mute the microphone? There is a feedback coming from some people. Thanks. So what we want to do in the area of synthesis is to actually now look at phase diagrams. For those who are not familiar, phase diagrams have been used for centuries by material scientists to design materials and essentially give you idea about pressure, temperature, composition, where you actually have that material existing. But there is a catch. Phase diagram only give information about materials at equilibrium. So if you basically think about the synthesis process, oftentimes during processing or during synthesis, materials are trapped in local minima, which are basically the metastable states. Okay, in the free energy landscape, these are states that often have very exotic properties compared to the materials which are there in equilibrium. And so there are many local minima that can exist for any given material, and it can exist in different forms, different metastable states. So the green dots are the metastable states, and often these metastable states are synthesized by accident. Okay, there's no map that allows people to actually look at these metastable states. These are very data intensive, but they offer infinite possibilities for us to actually look into. So we want to go beyond just the red dot, which is there in conventional phase diagrams, and we want to actually look at the red dots, the green dots, which are actually the metastable states that one can actually access. So I'll give an example of carbon, a material that most of us are familiar with. Carbon actually has more than 1,000 different metastable phases. So the first task, of course, is to identify what are those metastable phases. So beyond graphite, diamond, and amorphous carbon, there are at least 1,000 different bulk phases of bulk carbon that are actually available, and they are within 0.5 electron volts per atom away. So meaning that they can all be actually synthesized and seen in experiments. So the first task is to systematically explore these metastable states. You could either use a genetic algorithm in a structural way to actually identify these metastable phases, or what we are doing is to actually use more powerful techniques such as NCTS to actually operate in a in the structural space and identify these metastable phases. So our vision is that when you have a phase diagram, this is typically what you will find for carbon. If you look at a carbon phase diagram, you will see graphite, okay, pressure against temperature. You will find graphite, diamond, and amorphous regions. What we want to do is to introduce a scale, a free energy scale that allows us to actually now cut a slice through this landscape. So if we are interested in a material that is 10 MeV per atom above the most stable phase, we should be able to actually now see what those phases are. So in this case, if you go 10 MeV per atom above the most stable phase, you will see stacking disordered and hexagonal diamond. If you go even higher, you will now start seeing more metastable phases. So the idea is that you can actually start accessing these phases by providing external heat input or any other form of stimuli that allows them to actually be pushed to that local minima. And these are very much accessible, in terms of the energy scale, they're not too far away, but information about them is not actually present in most of the phase diagrams. So what we did, I showed you the schematic. We've gone ahead and implemented a workflow to allow us to calculate these different phase diagrams for metastable materials. And many of these actually could also be synthesized. So my colleague J.G. Van can actually do these high pressure, high temperature experiments in a diamond anvil cell. And he was able to actually take amorphous carbon and see many of these phases at conditions that we had actually predicted. So what our vision is to actually now take advantage of the the advances that have happened in the area of robotics and automation, and with an AI feedback and with these thermodynamic phase diagrams, and if we can map the kinetic conditions, we can now have a more autonomous synthesis of materials beyond equilibrium. So if you are interested in a particular property, and if there is a metastable phase that actually gives you those properties, you can navigate through these free energy landscape, and you can turn on the various processing knobs and selectively tune your pathway and arrive at a material that meets your desired target properties. And so that is something that we have a vision for, to move towards a more autonomous nanocenter. And with that, I would actually like to conclude my talk, and I'll be very happy to answer the questions that you have. Let me look up the chat and see if there are questions. If not, please feel free to ask. Once again, thanks for the invitation, and I'll be very happy to answer the questions.
Thank you so much, Dr. Subramanian, for this excellent talk. Yes, you can write, please, all your questions in the chat, or, well, you can turn on your microphone to ask directly to Dr. Subramanian, please. Thank you. There is a raised hand. I think, Fernando, you want to ask something to Dr. Subramanian? Yes, Fernando, you can open your microphone and you can ask directly, please. Thank you.
Sure. Yeah. Thank you, Liliana. Hi, doctor. This is Fernando.
Hi, Fernando.
Was a really amazing meeting. Thank you for this meeting. So, I just studied my PhD here at UNAM. So, but this is my last year. So I just study about gold nanoparticle. So this topic is very interesting for me.
Okay.
But I don't have any question in special. Only I want to ask you. I am looking for an opportunity to continue my research. I mean my postdoc, maybe after my PhD. So I really I want to have maybe a meeting with you. I don't know when you are available. So about because my idea is to continue my research about this. I last year I went to San Antonio to study and to do something about my project. So I know something about molecular dynamics a little bit because I am really focused about technique like microscope, you know. So that is why I am interested about your project.
Yeah, no, absolutely. I mean, I think we can schedule some time to chat, and I can also, if you send your CV, I can forward it to other people as well who might be interested. So
Sure. Thank you. Thank you so much.
Thank you so much. Someone else wants to open the microphone and ask something directly to Dr. Subramanian, or, well, you can write in the chat. I think one more question, Marcelino. You want to turn on your microphone? You can do it. Thank you.
Yeah, thanks, Liliana. Thanks, Professor Subramanian, for this webinar. It was really an amazing subject that you brought to us today. I have a question regarding to the correlation. For instance, when you take a physical or a molecule or atom that is known in terms of the size or properties, what is the correlation when you put it in machine learning model or a model, computational model? What's the correlation between the real size or the real properties and the computational model?
Yeah, so I mean, we actually, when we compare these cluster data, we actually go to as high as 55 atom cluster. But so, you know, we have all the way from dimers to 55 atom clusters. We compute their properties using DFT. And we try to actually have the empirical potential predict the same energetics for these 55 atom cluster. And so we have a separate training data and test data, and then we look at what the correlation looks. And in most cases, actually, the correlations look actually pretty good. But by going and including all the way up to 55 atom clusters, what we ensure is that, you know, we are almost going towards bulk-like properties. So even though we don't fit to bulk, if we evaluate the bulk, cohesive energies, lattice constants, to what we actually find using DFT, you know, from the model, the agreement is actually fairly, is actually excellent. So that's basically because if you go to higher sizes, then computation cost using DFT is much higher. But 55 atom already kind of captures most of these coordination that you're likely to experience. So that's one of the aspects that you need to train your model to reproduce essentially all kinds of local geometries or configurations that it is likely to encounter. So if it is able to do that, then it actually tends to perform very well.
Okay, thank you so much, and once more, congrats for the presentation.
Yeah, thank you.
Thank you. Someone else wants to open the microphone and ask something to Dr. Subramanian, or will write in the chat?
Yes, I have one question. Thank you so much, Dr. Subramanian.
Sure.
I have one question. How do you consider the defects like dislocations, stacking, faults, and etc. on the grain growth simulation?
So actually, we naturally allow these dislocations and stacking faults to form. We don't actually. So what we do is we start off from the very early stages of including nucleation. We track the whole growth process. So we first actually form these. Once the stable nuclei actually form, they grow and form these nanocrystal grains, and then we actually track what happens to. So these are simulations that extend over several microseconds, and the stacking disorder and all are energetically favorable, known to occur in ice, and those are naturally captured. In fact, in this particular case, we did not even train to those stacking fault energies, but it actually captures the relative energetics, even when it is not trained. In other cases, in metals, for example, you could actually train to those energetics, and you can make sure that the model actually works and does a good job at reproducing those.
Okay, thank you so much, Doctor. We have one more question in the chat. Mariana wants to know, in your opinion, this type of models, can you help us with reduce the number of experiments?
Actually, that is the goal. So the idea behind these AI-based feedback is that if you have, say, 10 different processing conditions, and if you want to basically map through and search, generally, if it is a grad student, for example, doing experiments, they will run through a more grid-based approach where they will try most of the combinations of these pressure, temperature, thermal history, and so on. And what the AI is actually good at is navigating through these high-dimensional space much more efficiently than humans can. And so in terms of the number of trials that is needed to converge to a solution, the AI will definitely help do a better job. And the idea is that you will learn from a few samples, and it basically learns from all the failed experiments and tries to navigate towards an area in the phase space where you can actually achieve your desired property. So yes, I think we have ourselves seen that you can actually converge much quickly depending on the algorithm and what it is designed to do. And so navigation through these parametric space, you will basically be able to achieve your desired targets with far fewer experimental trials, orders of magnitude lower with the AI.
Thank you so much, Doctor. Okay, this question is for me. They are asking if this seminar will be in YouTube, and the answer is yes. After 2 days, you will find in our YouTube channel, you will find a complete seminar, so you can brush up on the topic. And I don't know if someone else wants to open the microphone for asking Dr. Subramanian, or some more questions in the chat. We have one more question, Doctor. What software do you use for modeling 3D of grain size?
So that is actually an algorithm that we developed to be able to classify these different grain boundaries. So if you are interested, just reach out to us, and then I think we can share more details on how to use it and what needs to be done. But the classification algorithm is something that we just developed within our group. But it could be it could be a 3D characterization that can be done experimentally using tomography or other techniques, or it could be actually simulations such as phase field, or it could be finite element or other kinds of simulations where you actually are tracking some microstructural changes.